Okay, so depending on where the video cut off, sorry, we divided delta H by delta S, 348. This is the temperature at which the behavior changes. So this number line here represents temperatures from 0 to infinity. 348 is a dividing line. Now we need a test on one side or the other. Don't test like 347, okay? You know, what if you made some rounding error? You know, move away from this. Maybe like down to 200. Let's test 200. And what I mean by test is let's find delta G at that value. So delta G for this reaction at 200 would be the delta H, 72.4 kilojoules, minus temperature, 200 Kelvin, times the 0.2079 kilojoules per Kelvin. So at 200 Kelvin, the Gibbs free energy, 72.4 minus 200 times 0.2079, is positive 30.8 kilojoules. So down here, delta G is positive, so it's non-spontaneous for all of these temperatures, 0 up to 348. Then it would become spontaneous. I don't even need to do a test, as long as I believe I've done my math correctly. I know that that sign will now change, okay? And this is going to be spontaneous. So the answer to this question is, this reaction is spontaneous for all temperatures greater than 348 Kelvin. Okay? If you really want to be sure, you can test 400, test 500. You know, you should get negative values for delta G for those conditions then. All right, so you'll have proven both sides of it. But really, you should only need a test on one side or the other. Okay? Now, these two reactions are different, and we could have actually, without the test, we could have interpreted this same conclusion. This is an exothermic reaction. We've used Le Chatelier's principle to understand that as the temperature increases, an exothermic reaction shifts backwards towards the reactant side. Okay? Meaning it nowadays, now we would consider that to be less spontaneous. So as the temperature is getting higher and higher, this exothermic reaction is becoming less and less spontaneous. So that's why it was spontaneous for all temperatures below 3,916. The second example that I gave you, though, is an endothermic reaction, right? Temperature favors that reaction happening. So as you raise the temperature, it becomes more spontaneous. And what do we see? At low temperatures, it was not spontaneous, and it's not until we reach this 348 that it becomes spontaneous. Remember me mentioning the ice cube in class earlier today? How it will not melt in a freezer, but it will melt when you put it on a table, right? 0 degrees Celsius, 273, is the transition temperature for that process. Below 273, the ice does not melt. Above 273 now, the entropy starts to win. The delta S wins out, and that reaction becomes spontaneous, is what's happening in that case. All right? So that's what makes reactions spontaneous or non-spontaneous, is these two main underlying factors. The enthalpy coming from what bonds exist in the molecule, you know, how the pieces are put together, and then the overall picture of how that organization ranks relative to a perfect crystal solid. Okay? All right. I'm going to do one more of these transition ones to show you a neat case. Let's once again find the range of spontaneity for a reaction that has, let's say, delta H equals negative 42.8 kilojoules, and delta S equals positive 117.3 joules per Kelvin. All right. So if we're finding the range of temperatures, just like we did in these previous cases, we start with the transition value. Delta H divided by delta S. It's going to be negative 42.8 divided by, and that's in kilojoules, divided by 0.1173 kilojoules per Kelvin. Without even me doing the calculation, does anybody see a potential problem here? I'm going to have a negative Kelvin temperature, negative 365 Kelvin. In fact, that is a problem, right? Because a negative Kelvin temperature does not exist. So my number line of 0 to infinity, the negative 365 is way down here. I can't put it on there. Let the picture tell you what's happening then. So the dividing line is down here. So for all real temperatures, this reaction behaves the same way. I haven't said which way it behaves yet, but for all temperatures, it behaves the same way. That's the conclusion. When your transition temperature is less than 0, the reaction behaves the same way for all real temperatures. So now we need a test. We just need to test any one real temperature to figure out whether this reaction is either always spontaneous or never spontaneous. You might not even need to do that if you were paying attention to my comparative method earlier, though. I can go to Las Vegas and bet on this reaction right now, based on these numbers right here. What does the negative delta H favor for a reaction? Spontaneous. What does a positive delta S favor? So both odds favor this being spontaneous. They're not competing against each other. They're working together to make this reaction be spontaneous. So when I test a real temperature here, let's test 200 again, I better get a negative delta G telling me it's spontaneous. So negative 42.8 minus 200 times 0.1173. Yep, negative 66.3 kilojoules. So it's spontaneous, and we would say this reaction, our answer is that this reaction is spontaneous for all temperatures. Okay? So the fact that we get a negative sign here is more of just a, oh, heads up, don't make that your answer like you do in the other cases, because that's not a real temperature. It's a special category. All right? Now you're either always spontaneous or never spontaneous. If I flipped these two signs, made this positive and this negative, then we would be in the never spontaneous. We would get the same transition, negative 365, but our test would become positive 66.3, so non-spontaneous then, all right? And so we would say that it's not spontaneous for all temperatures, all right? So those are you can have a transition temperature and be below it when you're spontaneous. You can have a transition temperature being above it, spontaneous. Or you can have no real transition temperature and either always be spontaneous or never. Those are sort of the four possible outcomes for reactions. We saw 3 of the cases here, actually. Okay? All right. Now, Appendix 2B. Again, Appendix 2b is where these new standard molar entropy values are that you're going to have to start using to calculate some delta S's. Okay? You might have to use the delta H's as well because you might need to calculate a delta H and a delta S so that you can do a delta G. I was giving you the H's and the S's. The book will say, oh, you know how to calculate delta H on your own, so why don't you go ahead and do that as well. Okay? But that Appendix 2b has a third column of data in it, as it turns out. So Appendix 2b also has data for what it calls delta G subscript F with a little superscript. This is the standard free energy of formation. It's not exactly, but it's pretty close to doing a delta H minus T delta S for each of those compounds. All right. So it's what's the free energy when you form every single compound. And how have we used the two other values in that appendix? We've taken the H values, put them into Hess's law. We've taken the S values, put them into Hess's law. Guess what we can do with the G values as well? We can put them into Hess's law. So an alternative way, a different way to calculate delta G of a reaction then is Hess's law. Delta G for a reaction is equal to the sum of the free energies of formation of your products minus the sum of the free energies of formation of your reactants. What's not unfortunate, but what's limiting about this formula though, it's only good at 298 Kelvin because of the standard temperature being there. Okay? Whereas the other ones, the delta H and the delta S, while technically you're calculating them at standard, those don't change much with temperature. But free energy changes dramatically with temperature because of the entropy component changing. All right? Because of how many times we're paying that entropy tax or getting it back. All right? So we had the reaction earlier, 4 KClO3s to give us 3 KClO4 and KCl. So an alternative way that we could have figured out the free energy change of that reaction, I could have gone to Appendix 2b and looked up the delta G values. The delta G formations are negative 296.3, negative 303.1, and negative 408.5. These are back to being negatives, right? Because it's spontaneous to make these compounds. They will spontaneously form from their elements. That's what that's telling you in a negative value, all right? They're also on the kilojoule scale because these things are dominated by the delta H consideration, which is on the kilojoule scale. So just relatively, they're pretty big values, these numbers here, okay? So we could have, alternative to what we did earlier, we found the free energy of this reaction by H minus S. Now we can do it by adding up our products, 3 times the negative 303.1 for the KClO4, plus negative 408.5 for the KCl, minus 4 times the KClO3 value of negative 296.3. This gives us negative 132.6 kilojoules. In the interest of full disclosure, we got negative 133.1 earlier. We were off by 0.5 kilojoules. That's just due to a little bit of rounding. And then if you take a number that's been slightly rounded and multiply it 298 times, the rounding gets exaggerated 298 times. So that's why H minus TS will give you a slightly different answer than just this formula right here. Statistically, they're the same number though, okay? But you would come up with ever so subtly different answers using the two different methods, okay? So this becomes another way to get this. But again, it's only valid at 298. If you're going to do this at any other temperature, you're going to need H minus TS as the method that you use to do that, okay? All right. Now, so we've figured out today, we've done it quite a bit today, we've figured out what makes reactions spontaneous and non-spontaneous. It's this competition or this conspiracy to work together in some cases of the enthalpy, which is really derived from the bonds that are made and broken during a reaction, and the reorganization, the entropy of that system. And so this Gibbs free energy puts those two together with the temperature that tells us how many times the entropy comes into play to figure out if there's any leftover energy in this system to be given off. If there is, that's the free energy. That's what you can, it's going to be spontaneous, but that's also how much energy you can actually make use of for like heating a home or something like that, cooking, running any kind of other reaction that you might want to. That's what the free energy is going to be available for, okay? So that's it. It's a good place for us to wrap up. What we want to do next is get rid of this standard symbol. What if we're not working at standard conditions? What can we do then? How can we figure out the free energy? Not just temperature, but there are other things involved in standard chemistry. 1 atmosphere of pressure or concentrations being a particular amount. And it's almost never the case that we're working at that condition. So how can we tell, if what happens at non-standard conditions, is really an accurate picture of how this reaction is behaving. All right. So that's what we're going to pick up next, and we'll tie it all together to wrap this chapter up with equilibrium constants. How is this related to an equilibrium constant, since we spent so much time with that? All right. Thanks, and I'll see you in class on Friday.